we've got exams down here. They were ended back Friday. We went over all the answers on Friday. And then we did some live naming. Now we're going to go back over and review all the rules again, just to make sure we're all understanding it. And then how do we go about, we'll start thinking about approaches of how we go about naming, how do we identify what kind of compound we're working with. And that'll probably finish up our chapter, and we'll either start measurements and scientific notation today or on Wednesday. As we saw, naming ionic compounds containing polyatomic ions. So we either, for example, if we have KNO3, what we need to start recognizing is we're mixing a metal with a polyatomic anion. The NO3 is going to be part of our pattern recognition, or the NO2, or any of those that when we see several non-metals together, we should see if they form a group that we're familiar with, and they're going to be counterbalancing the charge of the metal in our compound. So we need to start recognizing what are metals and what aren't metals, and then when we have these groups of non-metals, do they form a common polyatomic ion that we gave a specific name to? So in KNO3, we can separate it into the K+, which is potassium, and the NO3, which we'll start recognizing is our nitrate ion. And so it's a neutral molecule because all of the positive charge of our potassium is being counterbalanced by the negative charge from our nitrate group. If we look at FeOH2, we split this up, and this is going to be harder because iron comes from the D block, the middle, our transition metals, and so it has multiple charges available to it. And the only way for us to know which state it is from our molecular equation, or molecular formula, is by recognizing this OH group. What's the OH group?
Base.
It's base, way ahead of where we're going to get. What's its name?
Hydroxide.
It's hydroxide. So, and what is the charge on a hydroxide? It's a negative one. And so we can see we have two of those, summing to a total of -2 charge buildup. It's a neutral ion, so that means we have to be dealing with iron 2 because that's how we counterbalance the -2 charge buildup from the 2 hydroxide groups. So it's iron 2 hydroxide is how we reference this. And so in the word, here we recognize that it's iron 2, so then we know from the name of it that we need 2 hydroxide groups. Whereas we use the reverse of that action from the molecular formula to identify the charge of our iron species. And then finally, if it contains 2 polyatomic ions, because we have a couple, very few, but there are a few positively charged polyatomic ions, we use the names of both ions. So in this case, we have to recognize that this is our ammonium group, and that's the nitrate group, so this is ammonium nitrate. And then we have our oxyanions, which we've been referencing again, which is when we mix oxygen and one of our other nonmetals. It becomes an oxyanion. Oxygen's a very electronegative element, which is why it normally forms anionic species, negatively charged species. And they get different names based on how many oxygens, as we covered. So the largest, the compound that contains the most oxygens for the non-oxygen element is the 8 ending, and the one that has fewer is the ite ending, except for in our halogen containing oxyanions. So we've talked about chlorine. When we mix chlorine and oxygen is where we get a chlorate. perchlorate, meaning one extra oxygen than the 8 ending, so it's ClO4. And the hypochlorite is one less than chlorite, so it's ClO. We can extend this to any of the halogens. We just change the chloro to bromo or iodo. Same rules apply, same naming conventions. It's still just pattern recognition. When we mix oxygens and halogens, we get extra amounts of oxygen-containing species, but we're going to mostly focus on just the chlorine and oxygen anions, because that's what we most run into in our day-to-day lives. If we don't have a counterbalance for our polyatomic ions, we should end them with the name ion to let us know that it's a charged species. If it's a neutral species, we don't include the word ion. So where do we run into these? I mentioned that we're only going to focus on the chlorine and oxygen ones because we run into it. The active ingredient in household bleach is sodium hypochlorite. So NaClO, that's what we call bleach. Baking soda is sodium bicarbonate. So again, NaHCO3, which is creates carbon dioxide gas in baking, gives bread products that lift to keep them airy. Calcium carbonate is the active ingredient in antacids. Use it to neutralize our stomach acid. Sodium nitrite is a food additive used to preserve packaged meats such as ham, hot dogs, and bologna. Sodium nitrate inhibits the growth of bacteria. It also binds to the heme molecules inside of red blood cells, making the meat appear redder, which is tastier to us. So, how do we go about naming molecular compounds? We've talked about ionic compounds. Now we're going to talk a little bit about molecular compounds. Again, we jumped in feet first on Friday. Now let's go back and review our rules. So the first step in naming a molecular compound is always, first step in all of our naming is identifying what family of compounds it belongs in. Just like naming ionic compounds, we need to recognize that it's ionic, meaning it's a metal and a non-metal. In this case, molecular compounds, we need to recognize that it's two or more non-metals. And we can learn how to name binary two-element molecular compounds we just use this form. We take the name of our first element, and we add a prefix telling us how many of those atoms are in the molecular formula. And then we take the base name of the second element, change it to "ide," and also add the prefix for how many elements are in that, atoms are in that molecular formula of that element. So essentially, for a case of CO versus CO2, we call this carbon monoxide, whereas this is carbon dioxide, telling us in this one we have one oxygen for every carbon, in this one we have two oxygens for every carbon. We could call this monocarbon monoxide, but it's one of those, if it's only one, we just assume, we can drop the mono and assume that we meant one. If it was more than one, then we would specify it. So this is the list of prefixes we should be familiar with. And so they tell us in words how many of each atom or or element, how many of each atom of a particular element we have in our binary compound. Yeah.
So I was noticing with some of the homework and stuff that like tetra and hexa and stuff like that, sometimes it just drops the A.
Yes. So even here, monoxide. To write it out fully correct, it should have been monoxide. But that's one, difficult to say, monoxide. And it flows better. So what happens is you drop the least important vowel. Right? For example, tetraoxide, somehow tetraoxide. We lose more information by dropping the O of the oxide, because then what's a xide? We don't recognize that. Then we lose by dropping the A there.
Okay.
And it's mostly just, I can't find a better reason than it's just easier to say.
Great.
In convention as holds that way. But yes, that does happen. I mean, it's generally when it's two vowels in a row, we try to drop it, except for apparently dies. So if there's only one element, like in the case of our carbons, we don't need to include the mono, because there has to be at least one, otherwise we wouldn't say it. And then we always label how many come for the second part. So CO2, carbon dioxide. The second element always has the IDE ending, as it's generally the most electronegative element in our binary system. So it's going to have more than its fair share of the electrons. The compound N2O, called laughing gas. What's the first element? How do we name N2O? I'm sure the answer's on the screen already.
Dinitrogen oxide?
Dinitrogen monoxide.
Oh, monoxide.
Because we have nitrogen, and we have oxide. But it's oxygen. It's the second element, so it's the ide ending. It's the second one, so we always specify how many we have. And nitrogen has more than two atoms in the molecular formula, so we need, or more than one atom in the molecular formula, so we specify two. Dinitrogen monoxide. My guess is, again, going back to when do we drop a vowel and when don't we? We can tell what, by dropping the mono, the last O in mono, we can still see enough of monoxide to know that it means one, whereas if we drop the I from dioxide, it would lose most of it's only two letters in the word, the prefix, so we lose too much information. And I think that's kind of the cutoff, is when we start losing information that we won't be able to tell what's happening, is what dictates when that trumps how easy it is to pronounce. Because triiodide doesn't necessarily roll off the tongue, but that's how we say it. And finally, naming acids. Again, first step is identifying it's an acid. Acids are molecular compounds that will form ions when dissolved in water. And as I was saying on Friday, we most easily recognize them because all of the positive charge in these ions comes from hydrogen. So it'll always start with a hydrogen in the molecular formula. They tend to have hydrogen in order to be an acid. This isn't we'll learn some different definitions, but for this point, at this time in the class, it has to have a hydrogen to behave like an acid. So we can categorize these into two groups: binary acids, which is hydrogen and one of our halogens, so group 7A elements, or oxyacids, which is hydrogen and one of our oxygen-containing polyatomic oxyanions. That's the short word. So those containing hydrogen, a nonmetal, and oxygen. Is that clear-ish? So how do we first recognize? Here's the flow chart of identifying acids. Formula has an H as the first element. That generally means it'll be an acid. HF, HCl, HNO3, anything that starts with a hydrogen will behave like an acid. So once we've identified that it's an acid, then we have to figure out, well, is it a binary acid or an oxyacid? And if it's a binary acid, there are only going to be two elements, hydrogen and one other element. If it's an oxyacid, it'll contain hydrogen and oxygen along with some other non-metal element. And as we saw on our sheets, binary acids are composed of hydrogen and non-metal. So we take the base name of the non-metal, so I should keep things in my hands. If we had, for example, let's do something wild, HI. And I think we did that on Friday. We'll do HBr. So first we have to identify the base name of our nonmetal. Bromine. We're going to drop the INE to add ic. Bromic, and then we put hydro at the front and acid at the end. So HBr, hydrobromic acid. So in our family of halogen binary compounds, we've got things like hydrochloric acid, hydrofluoric acid, hydroiodic acid. Where do we run into HCl mostly in our lives? Maybe. There's one that you live with every day.
Bleach?
Nope, stomach acid is HCl. Here's the first time we're seeing something new. You can see we have these parentheses with an AQ or a G after it. That tells us the phase that we will find this compound in. So the three common phases that we're used to seeing, we're hearing about, would be our solid, liquid, or gas phase. And so like G, HClG, that's gaseous hydrochloric acid. Then there's this other one that we use, AQ, that means aqueous. Aqua is Greek, I think, for water, Greek or Latin, one of those old dead languages. I guess Greek's not that dead. And it just tells us that our HCl is in a solution of water molecules. So there's a lot more water than HCl, but that still is present in our solution of water. So we could write, so if I were to write C12H22O11, that would be and then put aqueous at the end. That would be a solution of sucrose. These are sugars, so this would be a sugar solution that is salt dissolved in water. And then instead of having to say that there's water around, we just put the parentheses aqueous after the molecular formula to tell us what phase we can expect it in. Yeah?
But like the HCl, like aqueous and then the HCl, G for gas, that doesn't change anything with the acid at all, right? It's just
Nope,
like
it just
information.
tells us, yeah, it's just information for how we may expect it to behave or react with other chemicals. It will be a while before we really worry a lot about it, but it's being introduced. So, what would be the name of H2S?
So, it says it right there.
So, what's our non-hydrogen atom? Sulfur. It's a binary, so sulfur becomes ic. So this is hydrosulfuric acid because it's the binary version. So in this case, this hydro is really important because if we look here, sulfate gets so H2S is hydrosulfuric acid. H2SO4.
Ooh.
In these oxyacids are acids that contain, we'll get back to that in a second. Let's get all the rules out before we worry too hard about it. Contain oxyanions, we're learning a set of them. HNO3 contains the nitrate ion, 2SO4. So you can see all of the positive charges, all the negative charges of our oxyanion are being counterbalanced by hydrogen in these acids. And we're only going to worry about when it's all being by these hydrogens, because that's when they're the strongest version of the acid they can be. It's the best version of their acid, best selves. And so we can have more than one hydrogen ion, right? These are H pluses, and they will depend on the negative charge of the oxyacid. In the flowchart for naming oxyacids, is it anion counterbalanced by hydrogen so that we know it's an acid? Then, does it contain oxygen? Then it must be an oxyacid. If it's named, does it end in ite or ate? Because that changes whether or not we add the us or the ic acid. And this is where we get back to here. What is the base compound for this?
Sulfate?
Sulfate. So we drop the ate ending and we add ic acid. Can you see how these two names could be confusing?
But we don't have to put hydro.
Right, this is not a hydrosulfuric acid because it's not a binary system. The hydro helps tell us that it's the binary system, and that this is a very different compound than this. Just for practice, what would this one be?
Sulfurous.
Yeah, sulfurous acid, yep. Because the parent polyatomic or oxyanion is sulfite now because it's one less
Missing an
than
oxygen.
our sulfate. So so it becomes sulfurous acid.
I'm sorry, is it spelled just SULF or does it change to pH? No,
Oh,
no.
I think this depends on who is writing it, whether it's PH or F. Text wants PH.
pH, so it is pH.
In homework, but in the slides and stuff, it's not, and if you look it up online, it's not.
I think it's an older spelling with the PH, and we're moving towards F.
You gotta watch that.
So here is a list of our oxyanions
The slides came down a little bit. That one works.
in their base form, or in their ionic form versus their acidic form. And so you can see, if we recognize this part, where we see all of them start with a hydrogen, that's a good clue that we're dealing with an acid. Then we separate the hydrogen, try to figure out what the oxyanion name is. And once we identify that, we can get to its name. The harder part often is going the other direction. Well, what does an us or an ick mean when we see that alone? So we have to know these previous slide rules of how do we get there to know how we go backwards. So, if we had a giant flow chart of how do we deal with all of this, so we looked at all of them individually, these flow charts individually. Let's talk about it together, right? Because we're just going to be given molecular formulas that, or we'll run across them that we should know how do we deal with this information. So when we look at our molecular formula, we should be asking ourselves, is it a metal and a non-metal? Is it only non-metals? Or is it an H and some other non-metals? So hydrogen is the only metal and non-metal exempt. That's what turns it into an acid as opposed to just an ionic compound. And then we can follow down the flow chart. So if we see that it's a metal and a non-metal, we ask ourselves, is it a type 1 or a type 2 metal? Type 1 metals only form one charge of ionic species. So it's from like our first or second row columns of the periodic table. Right? Well, either in the first column it's always +1, second column it's always +2. Or is it from those pesky transition metals, group type 2, the D block, that can form more than one charge, more than one type of ion, because then we have to change the name a little bit. So if it's in type 1, we just call it by the metal's name, and then the base name of the anion plus ide. If it's a metal that forms more than one type, we have to change the name of the cation metal, or we take the name of our metal, add how many charges it should have. So is it iron 2 or iron 3? And then the base name of the anion plus ide, or the name of the polyatomic anion. If it's a molecular and it's only nonmetals, we just recognize that it's two nonmetals, and then we write down their names with how many there are, plus ide after the second element. And then acids are all of the positive charges being counterbalanced by a hydrogen. So, I keep specifying that because is this an acid?
No.
No, not for the purposes that we're working with right now. Because not all of the charges of our sulfate group are being counterbalanced by hydrogens.
So that would be ionic?
This is an ionic compound. And so we would, I don't think I put this on the short list of things to learn the name of, but that's what it would separate into as two compounds. I just want us to be aware that these things exist. And then for naming acids, we just. So, they give us a bunch of examples and then give us the answers on this next slide. CO, we can see carbon monoxide, it's molecular because it's only nonmetals. Carbon and oxygen are really close to each other over on the non-metal side of the periodic table. Calcium fluoride, calcium we can find in the second column, and fluoride is a very non-metal, so it must be ionic, and it's a type 1 metal, so calcium always forms a +2 charge, so it's calcium fluoride. HF, O, we're starting with a hydrogen, so that means it's going to be an acid. So then we ask what type of acid? It's binary acid, so it's hydrofluoric acid. We need to have that hydro to help us know that it's a binary acid. FeNO3, iron, it's kind of our ideal metal. When we think about metals, people think iron, maybe some of the other transition metals. But so this is one of those pesky type 2 metals, meaning we don't know exactly what its charge is. It can form more than one, so that means we have to look at its counter ion. What charge does the nitrate group have?
-1?
-1, yep. And so there are 3 of those, so this must be iron 3. So the name would be iron 3 nitrate. HCl4, aqueous, it's leading with an H, there's no other metals involved, so it must be an acid, it's an oxyacid, and it has the 8 ending, so it becomes perchloric acid. So the ClO4 minus was the perchlorate ion. We drop the 8 ending, add the IC, so it becomes perchloric acid. And then our last one, H2SO3, we just did it over there. We notice that it's an acid because all the positive charges go to hydrogen. Acid goes to an oxyacid. It has an ite ending, so it's sulfurous acid. So these slides are posted. You may grab this one, print it, have that in your notes for when you're doing these nomenclature types of problems to help get the thought process of how do I identify compounds written out. Chemistry and acid rain. So acid rain happens when rainwater mixes with air pollutants, such as the nitrogen monoxide, nitrogen dioxide, sulfur dioxide, that forms acids. So in that form, they are not our polyatomic ions, they're diatomic molecules, right? We don't have any charge listed, so they're neutral atom molecules, so they get named as a diatomic molecule. NO, nitrogen monoxide, and nitrogen dioxide, primarily from vehicular emission, combine with water to form what?
Hydrogen,
So it's HNO3.
nitric, or no, it's nitric acid.
Nitric acid, yep. How did we get that?
I almost said hydrogen before it.
HNO3, H is our cation, so NO3 minus. This is the nitrate group. 8 gets dropped, comes into the ick, and becomes nitric acid. SO2, primarily from coal-powered electricity generation, combines with water and oxygen to form sulfuric acid. They both will cause rainwater to become acidic, and so that would change the pH of rivers and streams. Some rocks are particularly soluble under acidic conditions, and some soil or some nutrients in soils are much more soluble under acidic conditions, and so are easier to wash away.
Formula mass.
So formula mass. How do we figure out how heavy our molecule is? Because sometimes that's nice to know. In fact, most of the time, we're going to be dealing a lot with the masses of molecules. So for any compound, the formula mass is the sum of all of the atomic masses of all of the atoms in its chemical formula. So what we do is, we look at the periodic table and grab the atomic mass of each element and multiply it by the number of atoms of those elements in our chemical formula, and sum it all up to get the molecular mass of any particular molecule.
The atomic mass is the red number, right? The
Yes.
bottom red number?
Yep.
Okay.
So let's start with something easy and familiar. What's the formula mass of H2O?
Hydrogen has one,
Hydrogen has 1,
and there's two of them.
0.009-ish, and oxygen is close to
15.1.
What is it? 16?
16. We're just gonna round and leave it at singles. 18. So yes, it is 18 AMUs right now. So this is hydrogen. We have 2 hydrogens times 1 AMU plus 1 oxygen and 16 atomic mass units gives us 18 atomic mass units. Rather than trying to figure out, what we did is we redefined the mass we knew a proton would be to be 1 atomic mass unit, so that we didn't have to deal with super tiny numbers. So if we had C6H 1106, I think this is glucose, C6. What's the formula mass of this?
Carbon has 12.
So it's 6 carbons
Times 12.
12-ish. I think I'm gonna just call it 12 for now.
The hydrogen
Times
has 1.
11 hydrogens times 1, and 6 oxygens times 16.
16.
Someone take that low hanging fruit. 5 is 50, so this is what, 60? 72. 72, that makes more sense. That feels right.
6 and 16 is 96.
It's 179.
Yeah, that sounds
Oh, that's 96.
That's
And
an
then the
oxygen.
total is 179.
96. 171? What?
179.
79. Yep.
Okay.
So it's as simple as, again, we always have a periodic table for our exams. There's a lot of information contained in there. We just have to know how to find it and how to use it. So, that is chapter 5, about how we name compounds and where their names come from. Questions on that? Yeah?
So on the worksheet,
Mhm.
for naming stuff,
Yep.
what is the formula for silicon tetranitride?
SiN4.
Ooh.
But is that balanced?
What was it again? What did you?
Silicon nitrate.
It was tetranitride, right? That's how you know it's 4.
That's how I figured out it's
Is it,
And then nitride
silicon acts like carbon, so it
is
would be
negative, or is
four
3 plus,
actually
right?
bonded to silicon. I didn't think that.
Jesus.
It's a good question. And I don't know if I have a great answer prepared. So this, yeah, SiN4, tetra gives me, is equal to 4. I means that it's just the nitrogen.
Because, so this is molecular, 'cause they're
Yep.
both nonmetals and it's just binary, or I guess I don't have to worry about that. Okay.
Does this,
What? I don't think it's balanced like molecule.
so like, if we try drawing the Lewis structure,
Yeah.
does it make a happy Lewis structure? Remember, silicon can go into expanded octets if we need to, but what we probably might see is something 2, 3, 4, 5, 6. Ooh.
Yeah.
Would it be
It's not
SI2?
meeting our octet rule, so I wouldn't ask us to draw a Lewis structure on this.
Or I put nitrogen on the
If it has to deal with 6, it will deal with 6.
Okay.
It can't go
Anymore.
more than 8.
Right.
It can't go into the expanded octet.
Like for,
And silicon only works for-
Yes, silicon can.
That's why everything after phosphorus, and silicon is right before phosphorus. Is silicon just like, weird one?
in order for that to be balanced, wouldn't I have to look at like nitrogen is 3 plus, right? Or 3 minus? Something like that?
Right now, nitrogen, we could treat it that way where you're starting to put charge. That's beyond the scope of what we need to worry about. This isn't an ionic system.
Right.
But if we treated this as a full -3 for each of them, that would be a -12. Silicon would have to
0.
It can only lose 4 valence electrons, so it can only go up to a +4 charge.
Right.
So each one of these nitrides is only behaving as a -1. If we're treating it as an ionic system, which is not what we're doing, because this is not an
Molecular.
ionic molecule, yeah, there aren't enough electrons in the system for us to reach our octets.
And then, cyanatic acid, HCN, is that hydrocyanic acid or cyanatic?
Only
Cyanide.
hydro, because we save hydro for just binary molecules,
Binary acids.
binary acids. And this would be either hydrogen cyanide or
Cyanic.
cyanic acid.
That's the answer they want in the cyanic acid's what they wanted in the homework.
They want it as a cyanic acid in the
Yep.
homework.
Oh, so, okay.
That's how I would rather see it, but
Then how would you write acetic? The one right below it, acid, would that be H then C, H3? Or would you put that extra hydrogen into?
acetic acid. CH, oop, get it right the other way. It's an organic acid, so I sometimes think of it, so it's OH,
C3.
C. 3?
Two, my bad, C2.
and I'll just go to the SLC and
Oh,
learn it.
Yeah.
would it be that way, or would you put an extra H into it?
Nope, it belongs out there. Because the chemical structure for this is that, and this is the proton that we're losing. Sorry, the hydrogen that we're losing in acetic acid.
Okay, and then very last one is hydrocarbon, because it's an opposite.
Carbonic acid.
Why are you so quiet? Okay, chilling. Yeah. I've started.
Any other questions?
Right.
Okay, well, then we're gonna hop into chapter 6. Measurements and problem solving.
Stuff online. Can you just pick your name over and over again, like some practice?
I got 100 on a biology test.
So we're gonna get
You
into
don't have to worry about those sorts of things.
how do we
The
talk about
commoners
numbers?
like
Because a lot of chemistry, we want to report results and data and numbers. How do we know how much to trust the numbers we're reporting?
yeah, there's no wait.
So uncertainty is indicated by the last reported digit. So if we're saying the uncertain, we will measure out to where we have to make a guess about our numbers.
I think we did this
You
in
always
lab.
measure out, so if we're looking, say, at a graduated cylinder, there are those nice clear lines on it. We know what those values are. It's the space in between where we have to guess. That's what uncertainty is. Is where you should take a little bit of a guess because you can estimate it, but that will have some sort of error bar, meaning it's within this amount of that last reported digit. So for example, in measuring global temperatures, the average global temperatures have risen by 0.6 Celsius in the last century. But what also needs to be said is that 0.6 degrees plus or minus 0.1 degrees Celsius, which means the data has an error of plus or minus 0.1. So the real answer could be 0.7 degrees Celsius or 0.5 degrees Celsius, but we know it definitely hasn't risen by a full degree Celsius yet. So it tells us what numbers are within an acceptable range and which ones we know we can rule out when we're talking about this uncertainty. And learning to recognize what is the uncertainty in values when they're being reported can really help us in making judgments about how much to trust the data. Because if this was 0.6 plus or minus 0.6, that could be anywhere from 0, it hasn't changed, to it's twice as much change as we're reporting, right? So these plus or minus values can be very important in the reliability of data. We're getting into political season and all the polls are coming out and they'll release these people are responding this favorably to each other, plus or minus this percent. Well, if those two percentages overlap, you can't really tell that there's any real difference between how the two candidates are polling. The other thing we're going to talk about is scientific notation, which is a way of reporting numbers so that instead of putting 10 zeros in front of my value, I condense it so that I can read it as 1.2, which is a number it's much easier for me personally to work with than this value. So 1.2 times 10 to the negative 10 is the same as 0.12. These are conveying the same information, and eventually they'll convey the same information to all of us. But this one is much easier for me to read and process than this one when I'm trying to compare values. So our decimal part tells us what the value is, what the actual number is, and then the exponent part, the exponential part, or 10 to the exponent, tells us what direction we need to shift our decimal place, whether it gets really big numbers or really small numbers. Because when we're reading and we're talking, we like to deal with things, between about 100 and 0.001 is generally where it's a sweet spot for what people want to talk about, read and say. So this is the value that we're recording. This is how large or small it gets. And, that's the slide. So when we say 10 to the n value, 10 to the value, it's just multiplying, it's just telling us how many times we multiply 10 together. So 10 to the 2 is, we could write it as 10 times 10. Or 10 to the 1 is 1 times 10. 10 to the 0 is cheating, because it's always 1. Anything to the 0th power will be 1. That's part of the definition of it. And so we can just see that it's whatever value times 10, so 10 to the second, 1 times 10 times 10, we get 100. If we put a negative, that tells us that it's the reciprocal, meaning it's 1 over that value. So to the negative 1 is 1 over 10. Negative 2 is 1 over 100, 0.001. So positive values will move our decimal point this direction. Now, they're telling us that our decimal point was over here, and we brought it this way. Negative value says our decimal point was here, and we brought it this way. So to convert a number to scientific notation, we need to find the decimal part. So that would be, in this case, this value. And then all we do is we count, well, how many times do I need to move this decimal point over? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And because I moved it this direction, it's negative. If I move it the other direction, it'll be a positive. And so